In section 4.6, we are exploring rank. So we're going to use our knowledge of vector spaces to look inside a matrix and explore the relationship here between the rows and the columns. So to get us started, we need to define the row space. So if A is an m by n matrix, we know that each row of A has n entries, and thus is identified with a vector in Rn. So we say that the set of all linear combinations of the row vectors is called the row space. And this is denoted as ROW, so row of A. So the row space is the set of all linear combinations of the row vectors. And two little notes before we go ahead and look at an example. The first is that since each row has n entries, the row space of matrix A is a subspace of Rn. So since each row has n entries, the row space of matrix A is a subspace of Rn. And last but not least, since the rows of matrix A are equal to the columns of the transpose of matrix A, then the row space of A is equal to the column space of A transpose. So we can say that since the rows of matrix A equal the columns of A transpose, this allows us to conclude that the row space of matrix A is equivalent or equal to the column space of A transpose. So to help warm us up, let's use the definition of the row space of a matrix A to explore this given matrix A. So looking at our matrix, we have 1, 2, 3, 4 by 1, 2, 3, 4, 5. So matrix A is an m by n, which is specifically defined here as a 4 by 5 matrix. So we can obviously conclude that there are m equals 4 rows and n equals 5 columns here. And since we're exploring row space, let's start by what are the row vectors? How would we define our row vectors so that they are not confused with the column vectors? So again, we have 4 row vectors here. The first row vector, r sub 1, will be defined as 2, -1, 1, -6, 8. Our second row vector is the second row, and we denote this as 1, -2, -4, 3, -2. The third row vector for this given matrix A is -7, 8, 10, 3, 10. And last but not least, the fourth row vector is defined by the components 4, -5, -7, 0, 4. And we'll keep in mind that these are also the column vectors of A transpose. Okay, so let's now look deeper into the definition of row space for our given matrix A here. And again, so we know, we've already observed that A is a 4 by 5 matrix. So what type of conclusions can we make from this? Well, since there are 5 columns, we can say that each row of matrix A has n equals 5 entries. So each row of matrix A has n equals 5 entries. We can also make a note that because each row has 5 entries, that each row can be identified with a vector in R5. So each row of matrix A can be identified with a vector in R5. And last but not least, using that definition, since each row again has 5 entries, we know that the row space of matrix A is going to be a subspace of R5. So the row space of matrix A is a subspace of R5. And that's again because each row of A has 5 entries. So last but not least, what is the row space of A here? Well, let's keep in mind that the definition of row space tells us that it's the set of all linear combinations of the row vectors. So we can say that therefore, since the row space of A is the set of all linear combinations of the row vectors, then the row space of matrix A is equal to the span of these 4 vectors. So the span of vector r sub 1, r sub 2, r sub 3, and r sub 4, because the span represents the collection of all possible linear combinations.